Hello everyone. Our mini project topic is path tracing. Our team members are myself Prachi Lohkare, Vikas Chaudhary, Paras Sarpute and Rupesh Panda. Path so Path tracing is an advanced rendering technique used to create photorealistic images. It simulates how light travels, reflects and refracts in a scene, producing realistic shadow and reflection. Unlike normal rasterization, it captures global illuminations, making the output look more making output look more richer. The problem with existing rendering so the problem with rendering the existing rendering method is that they miss indirect lightning effects. So our goal is to design a system that can handle multiple light bounce and generate realistic results. In our project, the defined object is sphere. Everything in our scene, whether it's ground, wall, or object, it is made of spheres. We use them for reflection, and light interaction as they are simple to define mathematically and efficient for rendering. Now, next will be continued by Vikas.
Now I will explain the concepts of ray-sphere intersection. Ray-sphere intersection is used to check whether a ray coming from the camera hits a sphere in the scene. This step is very important in ray tracing because it tells us which objects are visible and where shading must be calculated. To find the intersection, we combine two things: the ray equation, which gives us the position of a ray at any distance t, and the sphere equation, which represent all the points that lie on the surface of the sphere. When we substitute the ray equation into the sphere equation, we get the quadratic equation. Solving this quadratic tells us whether the ray touches the sphere and if yes, at what point. Now let's look at the mathematics behind it. A ray is defined as r of t equal to O plus Td, where O is the origin and D is the direction. A sphere is defined using mod of p minus c's whole square equal to r square, which means any point p that is exactly radius r away from the center c is on the sphere. We substitute p equal to O plus Td into the sphere equation. After expanding, we get a quadratic equation in the form at square plus bt plus c equal to 0, where a equal to d into d and b equal to 2d into o minus c, and c equal to o minus c into o minus c minus r square. So finding an intersection simply becomes solving this quadratic equation. Now let's see how we determine if an intersection actually occurs. We use the discriminant, which is delta equal to b square minus 4ac. If delta is less than 0, the ray misses the sphere. If delta is equal to 0, the ray just touches the sphere. That's called an tangent. If delta is greater than 0, the ray hits the sphere at 2 points. To get the actual hit point, we use t equal to minus b minus root delta upon 2a. Once we have t, we compute the exact hit point using p equal to O plus Td. To apply lightning and shading, we also need the surface normal at the hit point, which is n equal to p minus c divided by mod of p minus c. This normal is used for shadow ray, reflection and all the material calculations in ray tracing. So, ray-sphere intersection helps the ray tracer know where objects exist in a 3D scene, and it forms the foundation for shading, shadow calculation, reflection and many other advanced effects. Now Rupesh will continue with software and hardware requirements.
Hi everyone, today I will quickly walk you through the software and hardware requirements for our mini project on part tracing. Let's start with the software requirements. For the operating system, this project runs smoothly on Windows, Mac OS or Linux, basically any modern OS. We will use CPP, so you need a compiler like G++9 or above CLAC 10 or above MSVC 2019 or later. These versions properly support CPP 11 and onwards, which is required for our rendering logic. For code, you can use any standard IDE Virtual Studio Code C Lion, Virtual Studio, or Xcode as long as it supports CPP extension or CMake. To build the project efficiently, CMake is recommended but not mandatory. Since the program output images, especially in PPM format, you will need any basic PNG or PPM viewer to check the results. Op- Optional tools like Git and Python can help with version control or automatic script, but they aren't required for running the project. Now coming to the hardware requirements of our project. Part tracing is compu- computationally heavy, but this implementation is CPU based, so it doesn't demand a GPU. The minimum requirement of a CPU is dual core 2.0 gigahertz processor, but for better experience, a quad core 3.0 gigahertz or higher is recommended. On memory side, you can run it on 2 GB of RAM, but realistically 8 GB or more gives a much more better and smoother experience by rendering. Storage requirements are very light. Around 500 MB of free space is enough. Through using a SSD can help speed up compilation. You don't need a dedicated GPU for this version, but if you ever want to extend it with CUDA or OpenCL in future, a compatible GPU will definitely help. Lastly, any 720p resolution display is fine for basic testing, but a 1080p resolution or higher screen is recommended for better visuals of rendered output. That's it. These are the complete software and hardware requirements necessary to run or develop our part tracing project.
So, I'll be telling you more about our proposed system and the demonstration of our final product. This diagram shows the overall workflow of our renderer. We begin with a scene setup which includes defining camera parameters, lights, materials, and objects. Next, the ray generation stage emits primary rays from the camera into the scene. These rays interact with the objects, reflecting, refracting, and scattering following physical light behavior. Then we accumulate these contributions throughout our scene and store them into an image buffer which is then loaded by OpenGL. Next, you can see our implementation details. As you can see, OpenGL is not used for our rendering. Instead, it is only used to display our image buffer. We use functions like GLClear, GLVertex3F, and GLColor3F to draw each pixel to the window. ImGui also provides us with immediate mode GUI so that we can make our app more user friendly. Then, this is our project design. Our requirements are C++, OpenGL, GLFW, ImGui, and a PPM output. Then, let me show you more about our product. When you compile our project, you'll get a final exe, and when you run that, you will be seen with a completely user-friendly UI, and after you press the start button, it will start running the path tracing algorithm on 20 threads of your computer completely parallelly. We have recently implemented this multi-threaded. Now, if you wait for a couple of minutes, you will see a final image that looks just like this, and as you can see, it shows all the physical behavior of materials like reflection, refraction, and scattering of light. This is a completely physically based image. Thank you.